Well, it's really lovely to be here. It's a little bit early in the morning for me. My kids are still on their way to school. So if you see some children walking in behind me looking for socks or things like that, do forgive them. Um, so yes, as I was introduced, I'm a professor of hydrology at the University of Reading. I'm definitely not a mathematician. I do hang around with data assimilation scientists all the time, and I'm always confused. So you're definitely not going to get a lot of maths from me today, but hopefully I can still say something interesting that will entertain you in this hour. So I really love rivers. That's the first thing you need to know about me. Most of you, I'm sure, have a nearby river. They are all over the world. This is my local river. This is the River Kennet as it flows into the River Thames. Most of you may have heard of the Thames. That flows through London. It is just upstream from London where we live here in Reading. But this particular piece of river is brilliant because you've got the River Kennet flowing into the River Thames, and you get it circulating around as the two rivers hit each other, and they create these little eddies, little swirls and whirlpools that you can just watch for hours. And you get these shapes that look like hippos coming up and swirling around. And for me, rivers are so very beautiful. But they're full, they're full of these tiny droplets of water that we just don't appreciate. Most people kind of walk past this area of the River Kennet and the River Thames, not really even noticing the water. But of course, water is made up of loads of tiny little droplets that have fallen as rain. So when I pass this river, this spot on the river, I always stop and I always think, oh, look at all that water there. Where has all that water come from? When has all that water fallen as rain? And I tend to see the river as this kind of swirling mass of these little blue droplets. And they're a little bit like this in my head. I don't know if you can see this in the camera. It's a little blue glass droplet. And that's kind of how it looks like in my imagination. Billions and billions of these little blue droplets swirling around in different ways. And I like to kind of stop time and maybe freeze the river in time and look at each of those droplets separately. And I think, when did this particular droplet fall? Was it, last week when there was a little bit of snow here in Reading? Did that fall in that snowstorm? And then it's made its way slowly over the landscape and then down the river here to the Kennet mouth where the Kennet meets the Thames. Or perhaps it's been in the ground for like 3 or 4 years, or maybe even 4 decades, sitting in the groundwater and has only just recently been pushed out by that rain. There are so very many of these little droplets and these little histories, these little stories that are swirling around right now down at the Kennet mouth as the River Kennet meets the Thames. And this idea that all of the water in the whole planet, is swirling around and moving all the time, it really fascinates me. Rivers are very, very beautiful and very complicated, really very complicated indeed. And you can do this wherever you are, and I encourage you to do this at some point today if you can, or tomorrow morning if night has already fallen where you are. You can do this with a river, you can do it with a lake, or you can do it with a cloud. And just try and stop and close your eyes, and then reopen them and look at the water and see if you can see these little blue pebbles that I can see. This picture here is one of my favorite pictures. This is Lake Geneva, where you can see the clouds bubbling up in the afternoon in really exotic shapes. But of course, that's all water ripe for falling and ripe for ending up in the rivers that flow past us. And rivers are really complicated in other ways too. Very beautiful. This is the picture I've actually got on my desktop. I still have this on my desktop because I love it so much. This is a picture of the Amazon River, one of the coolest places I've ever been. I really recommend going if you've never been. But you can see this river from space so very clearly, but not just the main stem of the river, but also the tributaries, the little baby rivers, and then their babies, and the other babies of the babies as well, swirling around, meandering around, all of the old channel shapes, all of the complicated linkages of the river as this water, all of these little blue droplets, flow through this huge river towards the sea. So to me, rivers are very, very beautiful. I'm fascinated by them, but I'm also very aware that they can be absolute monsters, these beautiful monsters causing chaos and destruction. And everywhere, you know, in the world, there are floods. And every week, people are dying from floods somewhere in the world. And that's one of the reasons I'm very motivated to do what I do. So I am a flood forecaster by background, and I'm very interested in thinking about how we can understand rivers so that we can predict them better, so that we can deal with some of these very, very large problems. And of course, we know that flooding is getting worse because of climate change. Many types of floods are becoming bigger. Sometimes they're more frequent. And we're seeing parts of the world suffering from floods that haven't really suffered before. Some of that is because we've put more people in the way of floods, of course. But some of this is coming from these fingerprints of climate change on flooding. So I don't know if any of you have ever been in a flood. It is very terrifying. And there are lots of different types of floods as well. So this word flood, I know it translates differently in different language. It can mean lots of different things. It can mean huge areas underwater, homes completely inundated. It can be destructive and violent. It can have boulders and cars and trees, thick mud coming down and swiping through villages and into towns. It can mean people being rescued. It can mean people being trapped. And it can mean homes destroyed. It can mean homes unmade. That sense of safety that you have in your own home. I don't know how many of you are in your office right now, or if you're in your own home. I'm in my home office. I've just redecorated this office. It's got lots of my precious things in it. If flood water was to come into my home, it would be utterly devastating. As a flood scientist, I tend to keep my most important things not on the ground floor, because I've seen so very many people suffer when they've lost their precious photos or their precious items. But this is happening to people all the time. Their homes are really devastated, their lives are devastated and sometimes destroyed. So what can we do about this? Flooding is a terrible disaster all the time, all the way around the world. Well, I work with numerical weather prediction systems and Earth system models to try and predict floods ahead of time so that we can give people information to take themselves out of the way, to keep themselves and their families safe. And I do this a lot with ECMWF, the European Weather Centre, working on their numerical weather prediction model, a global model, thinking about how we can use these tools to get information that we can use to provide flood warnings. And we can predict lots of types of floods now. We're really much better at it than we were 20 years ago. We're certainly not perfect. There's lots more to do. But we can predict many types of floods before the rain has started to fall, even sometimes before the storm system has created itself properly. And that's because of the advances in numerical weather prediction. We've got some very good weather forecasts at the moment. If we have a big system coming through, like a tropical cyclone or monsoon rainfall, we can have a good indication that a flood is coming ahead of time. Sometimes when we have convective storms, like thunderstorms or other very, very heavy storms, we struggle a little bit more to work out exactly when and where that rain is going to fall, and therefore where the flood is going to happen. But we are getting much better, and a lot of that has to do with our data collection and the data assimilation systems at ECMWF, pulling in this weather data, the data in the ocean, in the Earth system, so that we can get the best estimate that we can of the weather and the land surface conditions, so that we can make a good forecast. And that's absolutely essential for what we're doing. Now, having hydrology, having water in an Earth system model has taken quite a long time to get going. Lots of weather forecasters were very anti-water for a long time, but I think they're coming on board now. And that's as all weather forecasting systems are beginning to move towards this Earth system approach, where you're thinking about the ocean, you're thinking about the land, you're thinking about pollution in the air, you're thinking about vegetation, everything that is an Earth system and not just the atmosphere sitting there kind of raining down or the wind blowing. And this is a really good time for thinking about hydrology, for thinking about where the water is in the land, because of these systems being linked, the land talking back to the atmosphere in these big models. What do we need to know as hydrologists? We need to know how wet the landscape is. That's really, really important for all types of hydrological processes. Getting at that soil moisture, working out the wetness of the river catchments. And we can do some of that in situ, but it's really quite difficult. So we rely a lot on remotely sensed information of soil moisture. And we also have estimates of snow cover. That's really important in parts of the world. We need to know how much snow is there, but that's really difficult and we get it very wrong a lot of the time. And often the data that's assimilated in the systems in the numerical weather forecasts are concentrating on getting the energy balance right, so that you can get the numerical weather forecast right. Whereas from a hydrologist, I want to know how much water is in that snow, when it's going to melt, and when that's going to turn into a flood as it runs down the river. So balancing the needs of a weather forecast for getting the energy balance right, so you can get the weather forecast right, and getting the flood forecast right because you need the water, is very difficult. Because what happens is people fiddle around with the snow cover in order to get the energy balance right, but that means there's the wrong amount of water in the snow. So the more that we can work together and work with systems that think about more than one outcome, the better. We've also got some exciting opportunities. So the SWAT mission, looking to see how much, where the rivers, lakes and reservoirs are all over the world, and feeding that data into our big models of where the water is on the planet will really make a big difference. So this is a very exciting development, being able to see how much water is in, for example, a reservoir from space, will allow us to say how much space there is for that reservoir to fill up if a flood comes along, or how dangerous it might be if a flood comes along and whether it might fail or not, and lots of these very interesting questions, as well as telling us, you know, what the water balance is so that we can make a better prediction. Other things, we saw the Amazon River earlier, one of my favorite rivers, really very complicated. Often when we think of a river, we think of one channel, we think of a nice neat channel that goes down and it's just one kind of tubular thing. That's how children draw rivers. But of course, rivers that don't do that, they braid, they bifurcate, and they meet again. And those flow paths, as the river splits and comes together again, can really change what's happening in our flood models. So one of the things we've been looking at is how you can really get to grips with some of these very complex river channels and put those into our global models of rivers, and that really will affect the flood hydrology that we get out of our river. And this is the work of the EVO Flood project led by Michael Wortmann, this paper. So for about 20 years, I've been working with the Copernicus Emergency Management Service for floods, the European Flood Awareness System, and its sister system, the Global Flood Awareness System. And this is a system that uses this idea that you can take these large-scale flood models and you can use them to provide early warning, so that you can take decisions to prepare for floods, to provide aid, and to support any other people who are trying to take these decisions. So EFAS and GLOFAS, they complement the national and regional services. So particularly for countries that don't have their own flood forecasting system or not a very sophisticated one, these types of services provide information ahead of time to help people take decisions on things like evacuations or moving aid around or asking for additional support. These systems started off just like kind of a PC a very long time ago, but now, of course, they're run on supercomputers around the world. So I've been working for about 20 years doing lots of different types of research with EFAS and GLOFAS. But the question is, I mean, perhaps lots of you don't even know what a flood forecasting and warning system looks like. Perhaps you've received a flood warning on your phone that says, you know, that there might be an amber warning, a flood might be coming, or in other countries you might get an alert that says, you know, you must prepare an evacuation pack or something like that. So how do we get from these big global models that are, you know, providing rain information that's then flowing down these rivers that we've got in our models? How do we get from that bit all the way down to that warning appearing on your phone and you perhaps deciding not to drive to your grandmother's house because the flood situation looks quite bad? So we have this diagram that you may have seen before called the valleys of death. It's not my favorite diagram, but it does help you understand what happens in these types of disaster management chains. We start at the top. So at the bottom, you can see these like mountain things. And we're starting over here, where it says observation. And that's the observations from satellites, it's the observations from grounds, from ships, from air balloons, every single type of observation that we have. In river flow studies, we have a lot of rivers around the world that are still measured with a stick, which we see how high the water has got by literally looking at a stick and seeing how high the water is. So we have a big problem in global hydrology. We have fewer and fewer gauges every year. Not enough information on river flow, definitely. So that's why using space-based information is so exciting. So we start with those observations. Obviously, that sets up the scene, those initial conditions of what we're doing, how wet are our river catchments, what's the atmosphere doing just before it starts to rain, and those kinds of things. And then we have our forecasting that starts in flood forecasting. We're interested in the weather, so we're really interested in the rain. We tend to not really pay attention to much else. So what's happening? We need these global models, and we need also downscaled local models to get the best weather forecast, particularly if we're trying to capture things like convective rainfall, where we want these very intense bursts of rain to capture exactly how much rain there is and exactly where that is. We do need a very detailed model, and even then it's still often wrong or very, very uncertain. And then once we've got that weather forecast, we need to turn that into our hazard forecast, so our flood forecast. And that's where we use these river models of how the water flows across the landscape once that rain has fallen through the soil, along those really complicated rivers until it reaches somewhere that we're really interested in. That tends to be a town where people live, or perhaps it's at a floodgate, so a gate that you might shut to divert water away should there be lots of flooding just about to happen. And then, of course, that's not the end of the story, because then we need to work out whether that's important or not, whether the river level has reached a level that is actually of interest to us. Do we care if it's this high, or if it's this high? You know, that's a bit worse, but you know, why is that important? And these levels are determined by, you know, whether people are going to be flooded. So we tend to have, I think around the world, there's normally about 3 levels. There's normally a kind of an alert level, which is a few roads are going to be flooded, and if you live near on a floodplain in an area of flood risk, you know, be aware that the river is very high and is coming out of bank. And then there tends to be a middle level, which is some of those riverside properties are going to be flooded. So there's isolated flooding often, but you need to be ready in case it gets worse. And then there's the highest level, which is there is danger to life. This is a severe event. You need to evacuate. You need to put your flood plans into place. So we often see these 3 levels. And that impact-based forecasting is really key, but getting the information ahead of time so you can work out exactly where these levels are on these rivers. It's really tricky indeed, and we often get it wrong. But it's much more useful to say to people, we expect flooding in your property than it is to say, oh, the river level is going to be 7 meters high, which is where we were really about 10 years ago. We were still telling people that the river level is going to be 10 meters high. So once you've got that, you've got your impact-based forecast telling, saying what the information is going to be, then you need to send those warnings out. And those warnings need to go to the public, to people who are in danger, who will need to take actions. So they need to be very clear on exactly what they need to do. But those warnings also need to go to local government, emergency management, and emergency managers. So they need to take those decisions too. And of course, all the way along this chain, we all know that our weather forecasts are uncertain and they are probabilistic. And that goes all the way down through to this point where you've got these warnings, but there is uncertainty around them. So how do you communicate that uncertainty? It is very, very difficult. And often it's done in a narrative form where there is some words that go alongside the warning that's saying the worst case scenario might be this. The most likely scenario is that it's not going to flood, but there is this worst case that there is a severe danger to life. But that's very, very difficult, and people get very upset because they don't get the information they think they need. They want a definite forecast of exactly when and where their home is going to be flooded, but we're still very much not able to do that. So there's lots of complications around communicating warnings. But that's not the end of the chain. There's another valley of death that we can fail at, and we often fail in this valley of death, and that's understanding people. People don't do what you think they're going to do. They don't understand things in the way that we think they're going to understand things. And they do things that, when we look at them, look very, very strange indeed. So, for example, there's a photo on this slide of a driving instructor. So he was teaching people to drive and drove into some floodwater. And as I'm sure you all know, you should never drive into floodwater because even a few centimeters of water can float your car. And lots of people die around the world. In the UK, we've had people die this year because they have driven into floodwater and their car has been washed away and they have drowned. And so this is a driving instructor who chose to drive into, it's by a ford. So in the UK, we have these things. I don't know why we still have them, but they are, where you drive through a river. And in the summer, that's fine, but in the winter, it's not recommended. And in flood conditions, it's definitely not recommended to drive into a ford. So people tend to do things that we don't expect them to do, and they also don't understand the warnings that the way that we think are going to do. So we start up the top with some observations. This is me doing my observations training at the Reading Atmospheric Observatory that we have running here, and it's got, it's been running a very long time, more than 100 years of data collected here. And I passed my training, you'll be glad to know. So if you see records from the University of Reading, that will be partly me reading the rain gauges. And also the diagram to the top, this is a hydrograph. So this is the way that we represent river flow in a probabilistic forecast of how much water is in the river. So river discharge, how much flow there is in the river, that's going up here on the y-axis. And as we go along ahead in time on the x-axis, we've got days of the week going forwards. And the little blue dot is where we're starting. That's today. We're going to make that forecast today. And we're going to go ahead of time, and we can see a flood coming because the river level, the river flow is going up, and then it's tailing off down again. And you can see the spread here in the forecast, the uncertainty in the forecast here. And these different colors represent those different thresholds, those different levels I was talking about earlier. And here we've got the purple zone we can think of as the severe flood warning zone. And we can see that some of our forecasts are going into that purple zone, into that severe flood warning zone. And that means there is a chance that there is a very bad flood coming. And that's really important, even though we know that many of those forecasts say that it's not going to be quite so bad. there is still this chance, and it's worth preparing for. So it's all about preparing for those worst case scenarios. And this is the thing that we really struggle with, is getting that information to people, even though the most likely scenario is that it's going to be a small flood. There is a chance that it's going to be very severe, and people's lives will be in danger. And the other photo I've got here is of some temporary flood barriers. I don't know if you've seen these go up. They're very, very clever. They still take a few hours to get up. But if we have good forecasts, we can put up these temporary flood barriers where we know people are at risk of flooding, and when we have those forecasts ahead of time to protect people's properties from flooding. So why do we do this? The UN has an initiative at the moment, early warnings for all. Why do we need everybody to have early warnings? Well, we know that it saves lives, and that's the absolute first key, is that we know that we can save lives if we have that information ahead of time. But also, you know, we do save money. That if we invest money in early warning systems, then that does save money from damages from floods in the long term. And so we've spent billions and billions of dollars, pounds, euros, pick a currency of your choice, setting up sophisticated flood prediction systems. And they, you know, these are big systems often, but they can predict when and where a flood will happen. And so that's why I work with the European Flood Awareness System and the Global Flood Awareness System, because we know that we can save lives and livelihoods. We don't always manage to, and that's a question I'll return to in a bit. I work quite closely with the Red Cross Climate Centre, and this is a picture of my colleague, Professor Liz Stevens, at the bottom. She's at the University of Reading and at the Red Cross Climate Centre. And Liz has been leading work looking at forecast-based action in the humanitarian community. How can we use systems like the Global Flood Awareness System to provide humanitarian actors with information ahead of time so they can take decisions to help their local societies and their local communities? And one of the first times that we tried this on a big scale was back in 2019, where the twin terrors of Idai and Kenneth, two tropical cyclones, hit Mozambique. Mozambique is one of the poorest places in the world. There are, you know, lots and lots of children under the poverty line, and you know, it just caused absolute destruction. However, you know, there was some action ahead of time because we were running these systems and because we could share this information with humanitarian communities. Tropical cyclone Idai was actually really, really interesting. It was one of these tropical cyclones that actually hit the country twice. It kind of made landfall, wiggled around a bit in Mozambique and Malawi, went back out into the Mozambique Channel, and then came back in and slammed into Beira. And there's a few tropical cyclone forecasts out for today in the same types of locations. So I'm always waking up in the morning and I'm quite wary that these things are ongoing, and we're still suffering from these big tropical cyclones. This was particularly bad because there was a large storm surge as well. So when the water gets piled up against the coast because of strong winds, coinciding with a high tide, coinciding with a change in the pressure, and that water will sweep in from the coast. So not only have you got rainfall flooding and rivers bursting their banks, but you've got flooding from the coast happening at the same time. So tropical cyclones cause an awful lot of flood damage. So Idai hit first, and then a few weeks later, tropical cyclone Kenneth came in and devastated the same areas. And when I'm saying flooding, I'm not talking about a few roads or a few homes being flooded. You know, it was a lot of the country basically looked like the sea, had turned back into the sea. And, you know, there weren't that many helicopters around, and there was a lot of people affected, a lot of people just living on the roofs of whatever buildings had not been damaged by the tropical cyclone. And this is, you know, this is a very typical picture from tropical cyclone damage. So homes have completely destroyed, roads cut off, and that's really important. If you can't get aid to people in villages who have been who have suffered from a tropical cyclone or from a flood, then that's a big problem. And working out where those evacuation routes are, where those routes are in to help people afterwards is really important ahead of time. So lots of damage, lots of destruction. One of the really bad things was the meteorological office in Beira was completely destroyed. And inside there were all of these handwritten climate records. And we can never get these back. You know, these are lost forever, which is why the digitization of climate records is really important. And there's lots of campaigns out at the moment, things like Rainfall Rescue, where people are using, you know, public citizen science basically to digitize lots of these handwritten records so that we don't ever get into this situation again. So here on the left is Janio Dambo. He's from the Mozambique Red Cross. He's kindly shared these photos and his stories with us, and we work quite closely with him, particularly in this storm. And some of the things they're doing here, so they have blankets, they have water purification tablets, they have water carriers, so containers to put fresh water in, and high energy biscuits and things like that. And the key is, if you can get these things to places ahead of time, then you can effectively save lives, because people don't suffer from those after effects of floods, particularly where you know communities will be cut off. Having this, all of these things in the right place before the tropical cyclone hits can really make a massive difference. So here is an example of some of the coordination that was going on, getting these products to the right people at the right place. And this is Janio. This is, I think it's quite a poignant photo, helping evacuate people from particular areas. And lots of this was done by boat along the coast. There was not the land-based transport, particularly between the tropical cyclones. So Idai had already hit, and we knew that Kenneth was coming towards us. You know, trying to get people out of the way or trying to rescue them as quickly as they can before the next tropical cyclone hit was very, very important. So this was a state where we used the GLOFASS forecasts to provide information ahead of time to the Red Cross so that they could work out where and when they needed people to move around and how they could take action. And it was, you know, it's really good that we could do that. You know, that's a really good start. That's the whole point of what I do most of the time. And it's easy to sit and kind of congratulate yourself about that. Oh, well done us, we're doing really, really well. But, you know, there was still a lot of people that died. We're still not getting the information to the right people. And this is across the world, we still don't do a good enough job. So there's lots more information that we need to get to people, and lots more kind of local support that needs to happen, and capacity building, particularly in those places in the world that just, you know, are so very poor. One of the things about tropical cyclones is everybody thinks, oh, a tropical cyclone, it's very, very windy. You know, you see these pictures of palm trees moving backwards and forwards and stuff like this. And that's what everybody thinks about in a tropical cyclone. And everybody's obsessed with the track. They need to know exactly where the landfall is going to happen. Like it's a tiny little spot that's, you know, that's the only place that's going to be affected by the tropical cyclone. But if you're thinking about flooding, that's definitely not true. We're interested in all of those spiraling arms of the tropical cyclone, because that's where the rain is falling. And even those pre-systems, those outer bands that can contain a lot of rainfall. And if those outer bands of the tropical cyclone hit first, and then you get more rain coming, that's an indication of big floods. But that track question is really interesting, because the track can move just kind of slightly, very, very slightly, and you can have most of that rainfall falling in a different river catchment, because river catchments are a bit like bowls. So if the tropical cyclone hits on one side of the bowl, all the water's going to flow that way. If it hits this bowl, all the water's going to flow this way. So really understanding how those tropical cyclones interact with the landscape, where the rivers are, and how wet it is already is really very important. And some work from Helen Titley at the Met Office, who is a PhD researcher at Reading, has really delved into this, about how how important it is to understand that hydrology in tropical cyclones, because the flood risk is one of the biggest risks from tropical cyclones. The wind is very, very damaging and very dangerous, but the risk from flooding is very serious. And we're continuing to work with the Red Cross. So my colleague Liz is leading on these two projects, on the Represa project, looking at tropical cyclones in southern Africa, and also thinking about floods on the White Nile, impacting Uganda and South Sudan, which are suffering quite a lot at the moment. So a completely different type of flooding, very slow onset flooding, where the lake levels just keep rising, and that then makes the Sud wetlands very, very wet, and the water just stays there sometimes for several years. So communities being displaced, and displaced, they're already displaced as well from conflict. So, this is a very important question. We've moved from the complexities of kind of water moving around the earth, and how difficult it is and how beautiful it is, but to the reality of what people need to know on the ground in order to keep communities safe. It's a big question, and one that I'm sure we won't find the correct answer to for a while, but we are making good progress. So what am I working on at the moment? So working with ECMWF, I like physics. Physics is very interesting, but at the moment, physics is not very popular. We all have to do machine learning because that's the way of the world. And machine learning is very powerful. And at ECMWF, I think I've got it on the next slide. Yeah, so ECMWF at the European Weather Centre, they are on their way basically to being world leading in providing machine learning based weather forecasts. And that's really good that, also thinking about machine learning based reanalysis products, just sucking in all the observation data into machine learning analysis of the atmosphere and the earth, and then thinking about how you can push that forward in time into the weather forecast. And I'm really interested in trying to keep hydrology up with that. Hydrology is really important. It's important because we need to understand our Earth system. It's important because it has feedbacks to weather forecasting as well, the evaporation, the snow cover. We need to understand it, also for climate studies, and also, of course, for flood forecasting. But machine learning techniques are at the moment only focusing on the atmosphere, only focusing on getting the kind of rainfall right, or the wind speeds, or the pressure levels. So we have a big project in the program that we're running at the University of Reading called Advancing the Frontiers of Earth System Prediction, to see if we can also use the same machine learning techniques to do things like flood forecasting, and also to provide that hydrological feedback into the atmosphere. It is very difficult, and it's a big project, and we're just starting, so I don't have any results to show you yet. I'll just skip that. So the question is, if we've got all of these sophisticated flood forecasting systems, and we're spending all these billions of dollars making all of that happen, and we're working with people all the way around the world, why are we still seeing so many deaths from flooding, particularly in countries that have sophisticated flood forecasting and warning systems? And two examples here, the recent floods in Valencia, just absolutely devastating, and there were good forecasts of both floods and rainfall out ahead of time. And then looking back to the floods of Germany in July 2021, a very similar story. We had good forecasts ahead of time. They were uncertain forecasts, but they were present. And we've seen that working in Mozambique, we can use uncertain forecasts to take good decisions. So surely there should have been more evacuations in these two cases. From my perspective as a flood forecaster, we had the right information we need. So why are so many people dying from floods? So let's quickly flip to Germany, where this is an example of the kind of map that you might get out of the European Flood Awareness System, the Copernicus Emergency Management System. And you can see here some of the rivers in Germany flagged up in that purple level, that kind of severe flood warning level. And this is a couple of days ahead of the big floods that happened in Germany in July. And I don't think it's that difficult to understand that if you can see lots and lots of rivers flagged up purple, that means that something bad is going to happen. Now, exactly which of those rivers are going to be the worst, that is not something that this system can do. But if you have a local running system and you're feeding it with localized information, particularly on the state of the rivers, then you have a more accurate forecast. And that's pretty much what happened in Germany. There was a local forecast that did show that some of these rivers, and particularly the Ahr River, which flooded very badly, had a big signal of a big flood coming. So a couple of days after I woke up and saw that forecast in the morning, as I did this morning with the tropical cyclone forecast for Mozambique, a couple of days later we woke up to scenes of utter devastation. And Germany is not Mozambique. Germany has flood forecasting and warning systems. It has a mandate to do flood risk mapping to make sure people know when they're on a floodplain and how things should have worked were certainly not how they did work. And lots of people died. And when lots of people die in a country that do have sophisticated flood warning systems, then there are questions to be asked about what is going wrong in those cases. And again, that's not the only case. So Valencia was another one that has such great similarities. People in local government saying that they weren't aware that it was such a dangerous situation. Members of the public saying they didn't know what they were supposed to do. The police saying to people they might want to move their cars, and those people got in those cars and then died because the flash flood came. So that's exactly what you should not do in a flood. So lots of things going wrong. And here in the UK, we've also had some recent very confusing messages come through because people don't understand the difference between a weather alert, which is for rain, and a flood warning that's coming from a different system and a different institution, and the confusing messages between all of these different systems and exactly what a yellow alert means. Does it mean, oh, there's probably nothing going to happen, so I don't need to do anything, which is what some people interpret it as, or does it mean, oh, be aware there might be some heavy rain coming? So lots of confusion in a recent event here in the UK too. So Joy Omar and our colleagues have looked into some of the reasons why people in Germany were not aware of the floods or didn't understand what was happening. Certainly there was some issues in local government and delegating responsibilities. There's lots of problems over there. But Joy in particular focused on residents, so people who had experienced the flood and reflecting basically on what it was like. And one of the biggest things that came through from the interviews that she did was that people could not imagine that flood in lots of different ways. They couldn't imagine that it would happen to them, what it would be like, what that would mean, what they would have to do, that it wouldn't be that big as well. If you've never seen a flood that is, 9 meters tall, I've never been in a flood that's 9 meters tall. Can you imagine that? It's, several houses high. That type of situation from in the River Ahr, and I went paddling in the Ahr this summer. It's very, very shallow. It's a tiny river. So it turns from this beautiful little trickling river into this raging beast, that is sweeping houses away. And that is incredibly difficult to imagine if you've never seen it before, or if the only floods that you've seen have been smaller floods, then you expect the next flood to be that smaller flood, and you can't imagine anything worse. But also just being in a flood and the reality of it, and knowing what to do, knowing how to get yourself out of danger, and also understanding the uncertainty as well. So this is that it might happen, but it might not happen, because we have that uncertainty in our weather forecasts and our flood forecasts. And all of these questions about being able to imagine, being able to perceive the risk that you're in, we are still a very long way from perfect when it comes to these systems. So my question is, what is the use of a perfect forecast with perfect data assimilation techniques if people can't understand the danger they're in, And those warnings that came out at the end are then entirely useless, because even though the warnings may be perfect, people are choosing to do the wrong thing. So this is the biggest question, I think, at the moment. It's one of our biggest challenges. We can have the biggest computer models in the world, the most sexy supercomputing systems. But if people don't know what to do in a flood, or they can't imagine the danger they're in, then they're entirely pointless. So we've got lots of opportunities. We've got the opportunities for machine learning. We've got lots of very clever people working on weather forecasting and flood forecasting around the world, and that is great, and that's brilliant. And we've got this, machine learning in particular, I think, has a lot of potential here to transform things. But I don't think any of that is worth pursuing unless we can also help that blossoming of imagination in emergency responders and in members of the public. So I'll leave you with that thought. Thank you very much for listening.
Yeah, thank you very much. I found it very interesting and inspiring. We will see if we get questions so please, from the audience, if you have questions, please write them in this UPED website. I start asking questions because I came to two questions. One is actually linked to this case in Germany. Since I'm in Germany, I'm not close by there, but in Germany, I kind of heard that actually some of this disaster and the many that people came from, that basically the local politicians, they were kind of overwhelmed by the situation. I would need to react, so I can't, so I rather don't do anything. So that's why I wonder, how is it in UK? How far do you see that kind of politics when you do advice or so is really able to taking this up and perhaps learning or being better prepared to react in such a case?
Yeah, I mean, so there are similarities and differences. Germany is very complicated. I have to say, everything is, divided into Länder, and then the responsibilities are delegated down to, for in this case, sometimes the local mayor, was responsible for the local evacuations, and other politicians who were making bigger decisions on kind of on the state level were distracted by other things, shall we say, to be polite to them, and didn't understand that danger. I think if anybody had understood the risk effectively, they would not have ignored it. I don't think it was I'm not sure it was a case of being overwhelmed. I think it was a case of not being able to imagine it was going to be that bad. It just looks like a bit of rainfall. And so that understanding of what might happen, in the UK, we are very fortunate in that we have a national flood forecasting centre, which is a collaboration between the Met Office and the Environment Agency, who are responsible for flood forecasting. And they provide information directly into different levels of emergency management, including advice on this type of thing. So I think that in the case of the UK, it's not perfect and it does go wrong sometimes. There is a lot more support for the people who have to make those decisions. So they're not left on their own going, what do I do with this? It says there's, a forecast of 7 meters in this river. That's surely a mistake, or I don't understand this weather forecast. There's a lot more support available. And that, that's a very big simplification. And, the German Weather Service and the local forecasters did try in the realms that they had to provide that information, but the structures in Germany are much more complicated, and it's much more difficult to give those types of support. And there is no hope, I think, absolutely no hope of having a national service for flood forecasting, because it's out of the remit of the German Weather Service and it's delegated to those local ways. So that's a bigger problem. That's a real problem about governance, of being able to provide flood risk information.
Yeah, thank you. Since there is no other question, let me, on a more technical level, actually, like so I'm not hydrologist, so I just some have some colleagues who do data estimating hydrology, so I learned just a little bit. But where I wonder is with when it comes to for the river, say hazard forecast, how much? And we had this last winter here in Germany that we had in the north quite some flooding, where the rivers are rather slower. So how much does it really depend when you do such forecast? What maybe you have a weather forecast? How much does it depend on the weather before? So does it matter how much does it matter that the soil, that the ground is wet or so, or in the other extreme cases, it's just the surface runoff and then the river is getting flooded? So how much does it play a role and how is this taken into account in the models?
Yeah, it's massive. It's massively important. It's really, really important. So having the previous weather forecasts right is really very important. So if it's like a kind of the sponge analogy. So if you have a wet sponge, the water won't go in anymore, just run straight off. And when you have water running straight off the landscape very fast, you can have a very big flood because it's very, very sudden. All the water is collecting together and it's very, very high indeed. And that's true of big rivers too. So in smaller rivers in the mountains, we will have flash floods that will happen in a matter of hours. And we saw that in Valencia and in the R Valley. You can literally see the wall of water coming towards you in some of those videos. On the bigger rivers, they are slower, but they will build up to these big floods. If the whole landscape is very wet, you've got all those little rivers feeding in those kind of very fast flash floody bits, and then the big river rises like a big monster. And so having that understanding of how much water is in the soil, how much water is in the rivers to start with is really key. Now, how much water in the rivers to start with is the one that we're really bad at, I think. They're all quite bad, but we're quite bad at that because we don't have enough measurements. Because our models are not perfect, getting those initial conditions is really difficult indeed. And that's where post-processing or our ability to know where our biggest errors are ahead of time is really important when we're setting up our models. But we also need the weather forecast before to be right. And that's something that we've got a lot better at, I think, in linking up weather forecasting models and flood forecasting models.
Yeah, thank you. Actually, with these models, so what type of data is typically assimilated and what is just taken as forcing? So weather rain is usually probably forcing for the model. So what type of data is typically assimilated for such?
Yeah, so it does depend, right? So I work with two different types of model. So if we're using ECMWF's model, the idea is that it's just the Earth system. So everything is being assimilated as possible. So soil, including soil moisture, and not quite yet, but we're nearly getting in river flow measurements, river height measurements as well from space. And also those flood inundation maps. So when you look down on the landscape and you can see the outline of where is inundated, and that helps you calibrate that model for next time so that you can understand the flood is coming. So, and that's great, but most flood forecasting models around the world don't do that. They just use the rain, and then they stick them into another model. And there are measurements that are going in. So that's the measurements of the river height. That's the most common thing that goes in, and very little else goes into those models. Sometimes you have the calibration beforehand, where you will use soil moisture and you will use lake levels and other hydrological variables to do that calibration before. But then in real time, pretty much nothing is assimilated, and that's often because we're still using very simple models. The Environment Agency here in England uses very simple models because it doesn't have the computational setup that it needs to run more complicated models. And also, if you're running an operational model, it has to be absolutely robust, and everybody has to agree that this is the best way to do it. And therefore, to change to a new way of doing something is really, really hard. So even though I've been pushing for at least 20 years to do something differently, in England, we're still not using probabilistic flood forecasts. And we are still using very, very simple local models in order to make these forecasts. But, we do what we can.
Yeah, Thank you. I think we have to move on. So thank you very much for your interesting presentation. Let me stop the recording.